during my last year of PhD at Chicago, Chandra's recommendation, I spent about quarter year spent between the CTS, the Center for Theoretical Studies, at this institute, and the institute. And I have the fondest memory of that time. So today I want to tell you about general relativity and its discovery and how it has evolved. Now, generally when one gives such public lectures, one usually focuses on some recent development, exciting advance that have occurred in science, and spends time explaining it in general terms but to a wider audience. But time to time, it is sort of it's good, I think, to change this style a little bit and take a subject like general relativity and give a perspective which is very, very broad, right? Basically, advances that occur over 100 years. And as we'll see, this kind of a perspective tells you how non-linear the evolution of science is. Particularly to the young people in the audience, and many of you here, I'm very happy about that. Many of the things that you hear today and you study today may seem like obvious to you and may seem like it was always so. And we will see that that is not the case. You will see that big mistakes were made and then they actually changed, then they were corrected, and these corrections changed the course of science. I find that even for myself, as a senior researcher, such broad perspectives are also useful to sort of say, provide a campus, because sometimes you are so involved in your work that you don't have this broad perspective about how science actually evolves, and that actually can make you reformulate your broad research goals and interests. And so I hope that this goal is my goal, and I hope it is okay with you. Then, let me then begin. Basically, in this talk, what I want to provide you with is a bird's eye view of the discovery and the deep impact of general theory of relativity. Well, I will only be able to focus on what is called classical general relativity and not the quantum aspects of the theory, which are dominating in the last many years now, maybe 2 or 3 decades now. Actually, Mukunda mentioned about this Dirac's theory of constraint systems, and that was actually a beginning of this quantum theory of gravity. But I gave a colloquium this morning on that topic, so I don't feel too bad about missing it out. And even in the classical theory, I'm only going to provide you with an impressionist portrait. The talk is in 4 parts. First, I will tell you what general relativity is about, how it was discovered. Then we will see that general relativity led to the cosmology, what we today call about the size or the large-scale structure of the universe that originated with general relativity. Then I will tell you about black holes, and then I will tell you about gravitation waves, and then summarize. Okay, so let's begin with the history. How was general relativity discovered? As you all know, in 1905, Einstein discovered special theory of relativity. At that time, he was still working in the patent office as a clerk. And in 1907, he was still in bed in the patent office. And he was asked to write a review article on special relativity. And this was for a journal, which was an annual reviews kind of journal, from Göttingen. And Einstein, there's a very moving letter that Einstein wrote to the editors, saying that, well, since he works in the patent office, he is off only at 5 o'clock, and by 5 o'clock all the university library is closed. So he has not been able to keep up with the literature. He doesn't know what exactly happened in the last couple of years, so could they provide him with some of this literature? I mean, it's very beautiful, moving story. But when he was starting writing this review article, he realized that there is actually a tension between special theory of relativity and Newtonian gravity. Professor Mukunda mentioned about Maxwell's discovery of unifying electric and magnetic forces, and then it really was a tension between the electromagnetism and Newton's notions of space and time, and that tension was resolved through special relativity. But then Einstein realized that there is a new tension. Einstein changed the notions of space and time in special relativity, and in special relativity, distance simultaneity of events does not make any sense. There is no absolute time. Time depends on the state of motion of observers. But in Newtonian gravity, as you know, if I look at this pointer and if I move it, then the gravitational force exerted by the pointer at the back propagated instantaneously. And that is not compatible with special relativity. So Einstein began thinking that we need a new theory of gravity. And therefore he wanted to know, in fact, to resolve this tension, should we actually change our notions of space and time and of gravity once again. Then Einstein was continuing to think about this in a single-minded way. And in 1913, by then Einstein was professor at the ETH in Zurich, and Max Planck, who was founder of quantum mechanics and senior German physicist, came to Zurich to convince Einstein to move back to Germany, to Berlin, and they were offering a very nice offer with 3 positions at the same time and so on. And all this administrative talk was first conducted, the terms of the offer were explained to Einstein and so on. And when this was done, Max Planck asked Einstein, so what are you now working on? So Einstein said that he is looking for a new theory of space, time and gravitation. And Max Planck's response to that was, as an older friend, I must advise you against it. For in the first place, you will not succeed. And even if you did succeed, no one will believe you. And this is coming from Max Planck, not some random person, the senior physicist of them coming from that. So this shows how ahead of time Einstein was, how much, even leaders in physics were completely unaware of it. But fortunately for us, Einstein persisted, and 2 years later discovered general relativity. Oops. And then the final paper Einstein sent to the academy, the Russian Academy, on the 26th of November. And on the 28th, he wrote this letter to Arnold Sommerfeld, who was, the eminent theoretical physicist. 8 of his students got Nobel Prizes. He himself was nominated a couple of times. And Einstein wrote to him, as was said, Professor Chatterjee, this really is a hard subject, and Einstein had to exert himself enormously for 8 years. And particularly the last couple of months, he had heard a lot, he had worked extremely hard, and he said, during the last month, I experienced one of the most exciting and one of the most exacting times of my life. True enough, also one of the most successful. And Einstein discovered the final form of the equations of general relativity, and then applied it to a problem that had been opened. And the problem had to do with the motion of Mercury. There was a certain anomaly in the motion of Mercury that had been known. It was very tiny. It was only 43 minutes of an hour per century. But it was well established. And Einstein found, to his delight, that when he applied equations of general relativity to the motion of Mercury, he found he could account for this discrepancy. In other words, he could account for the observed value. So Einstein was very excited about it, and he wrote to Sommerfeld that. So what is this beautiful theory of Einstein's all about? So let me have just a summary in one slide of general theory of relativity. So the basic idea is the following. See, people started thinking about space and time long time ago. I mean, Buddhist literature, Hindu literature, Greek literature as sort of treatises on the nature of space and time. But for those 2,500 years, space and time was always an arena. It's like a stage on which things happen. The stage is not an actor. Right? The stage is just sitting there, and things happen in the stage. So geometry of space and time was just a stage on which things happen. Planets move, electromagnetic fields propagated, and so on. Well, with general theory of relativity, that changes. Space and time becomes a dynamical entity. It becomes like this pointer, or like those chairs. It can be acted upon, and when you act upon it, it moves, it changes its state, and it reacts back. So space-time geometry becomes a dynamical entity, like all other dynamical entities, physical entities that we are really aware of. So why does this occur? It is because the gravitational field itself, the Newtonian idea of gravitational field, so to say, disappears in a certain way and is encoded in the very geometry of space-time. So if you have a massive object like sun, it bends space-time, it warps space-time around it, it bends it, and so to say that bending encodes the whole effect of gravity. And then when test bodies like the Earth move around each one of the bodies, if you like, in a literal sense, these bodies in space and time try to move as straight as they can, so-called picture of Einstein is really everything is encoded in this bent geometry. Now why is this possible? Why is it that gravitational force can be incorporated into the geometry of space-time and not, for example, the electromagnetic force? It is because gravity has two characteristics which are unique. First, it is omnipresent. You see, I can build cages, I can build these rooms where there is no electromagnetic field at all, basically because I have both positive and negative charges. But there is no place in the universe where there is no gravitational field at all, because there is always mass, and there is only one side of mass. And there is always gravitational field everywhere. So it's omnipresent, just like space-time geometry, which is omnipresent. And the second thing is that it is non-discriminating. It acts on everything exactly the same way. Doesn't matter whether it is copper or gold. Doesn't matter whether it is positive charged particle or negative charged particle. Doesn't matter if it is a nuclear particle with certain quantum numbers or another nuclear particle with other quantum numbers. Gravitational field acts on them exactly the same way. Just like geometry. And that is the reason why gravitational field and only gravitational field can be absorbed into the very geometry of space and time. And then matter, as like the sun, for example, tells space-time how to curve, and space-time tells matter how to move. So geometry is intertwined with matter via equations that Einstein discovered. So this was a really fabulous idea, like a totally, completely different kind of idea, and changed the perspective in time. And this was recognized quickly by the towering intellectuals at the time. Hermann Weyl, a leading figure in physics and mathematics both, wrote one of the first books on general relativities, in space, time, and matter. So here is a quote from Hermann Weyl. He says, "It is as if a wall which separated us from truth has collapsed. Wider expanses and greater depths are now exposed to the searching eye of knowledge, regions of which we have not even appreciated. It is as though we are all enclosed in this room and the curtains were all drawn, and we are just accustomed to this room. And suddenly the curtains were open, and out there was beautiful vistas. Suddenly we became aware of it." So that is the sentiment that leading people had with Einstein's theory of general relativity. And here is a beautiful quote from Chandra. It refers to Henry Moore. Henry Moore was one of the leading sculptors of last century. His sculpture, Atomic Energy, is on the campus of University of Chicago. And Henry Moore visited University of Chicago. So Chandra says, when Henry Moore visited the University of Chicago some years ago, I had the occasion to ask him how one should see sculptures. Now those of you who know Chandra can appreciate that only Chandra can ask such questions, right? How one should see sculptures. Should one see the sculptures from far, or should one see them from nearby, from close? And Moore's response was, the greatest sculptures can be viewed, and indeed should be viewed, from all distances, because new aspects of beauty will be revealed at every scale. And he gave an example of Michelangelo, and this is La Pieta of Michelangelo, which is in Vatican. And in the same way, now Chandra says, the general theory of relativity reveals strangeness in proportion at every level in which one may explore its consequences. This phrase, strangeness in proportion, comes from William Blaise, that Chandra liked enormously, which has to do with what is a sign of true beauty. The true beauty should be a little bit strange, but the strangeness should be in proportion. And this is what Chandra had to say about general relativity. Now, this is not very beautiful, but one might say it's so abstract, right? Space and time bend and curve and all that. I mean, in some sense, why would ordinary people care about it? Why would general relativity become such a sensation that everybody suddenly, Einstein becomes a household name? Well, this happens in a very curious historical almost accident, right? And this is important for people who want to think about science, how science evolves and how things happen. What happened was basically the following. Arthur Eddington, very distinguished astrophysicist in Britain, happened to be also a Quaker, and therefore he was a pacifist opposed to war and violence. So he did not want to fight in the First World War. He was prepared to go to prison as a conscientious objector. But the Royal Society, but the Astronomer Royal thought that this was really, could not really happen, and therefore what he did was to find a mission for Eddington, in order to send him on the mission so he doesn't have to fight in the First World War. And this mission was to verify Einstein's theory of general relativity. And this was going to be happening by traveled to a certain island of West Africa, where, in fact, one was going to see a total eclipse. Now, why was this important? Well, as we saw a couple of transparencies back, what happens is that if you have central dense object like sun, then space-time bends around it. Now, if I have a distant star and the light is traveling towards me, coming from this side up here, then this light actually goes down and comes back again. And so to me, it appears that the star is somewhere, you know. Now, if this is sun and this is earth, and now if I go up 6 months later, I'm on the other side of the sun, facing the star again, then you can see that the light is going to not go through this curvature of sun, and therefore the star will appear to be somewhere else. So by observing the star from the two sides of the sun, so to say, one can tell if in fact light is bent according to Einstein's theory. But this of course requires total eclipse, because one time when you are looking at the star, the sun is right in front of you, and of course you have to face the sun because the star is on their side. If you face the other way around, you're back towards the sun, then you don't see the star. So you need a total eclipse there, and that's why Eddington could go and was sent on this mission. He did go there, and he confirmed Einstein's theory of general relativity. Those of you who are experts in the subject may have heard that a lot of people thought that Eddington's error estimates were not correct and so on. As it happens, just in the last couple of years, real experts have gone back and looked at Eddington's data, and that confirmed that what Eddington said was really true. This is just a slight remark for you. Okay, so this is what happened. And then suddenly, Einstein became a household name. Why? Well, we were at the end of the First World War. The world was tired by human stupidity, all this violence, all these divisions between countries and so on. And here was science, which came and stood away like a tower, right? Like a beacon of light, which was away from all this stupidity. A theory which was discovered in Germany by the German scientist Einstein during the war was verified by British astrophysicists, the other side of the war, and was confirmed. And so overnight Einstein became a celebrity. Here I just happen to have the cover of New York Times on 10th November 1919. And the headline says, "Lights all askew in the heavens. Men of science more or less agog over the results of the eclipse observation. Einstein's theory triumphs. Stars not where they seem to be or were calculated to be, but no one need worry." So this is what happened. And suddenly Einstein became a part of the general culture. So this is how often, this is not related to hard science, but we are human beings. Science is part of the human endeavor. So these are beautiful, and Einstein's theory is fantastic, and it all works. But there's a tautology fact that this is an austerity, right? So most of the theories say, yeah, they're all very beautiful, but what does it matter? I mean, what is the practical use? Well, I think that this theory offers a very interesting lesson for all of us. Namely, fundamental laws of nature always matter. Why? An outstanding example is the global positioning satellite system that we use in our cell phones every day. Absolutely every day. Cell phones would not function because of that. There are a bunch of satellites. They are sending light signals, and because there are several of them, they track your device, and by looking at, because there are several of them, they basically provide coordinate of where you are. But in order to do that, these clocks on these satellites have to function properly. Now it turns out that because the satellites are moving, their clocks tick at a different rate than your clocks on Earth. But also because satellites are are high up, where the gravitation field is weaker than where we are. Because of bending of space and time, the clocks tick here at a different rate. It's a physical fact. Clocks tick here at a different rate than they tick out there. And you have to take into account this effect. If you did not take this into account, then in fact you will get errors. And one would say, oh, yeah, that error may be like 1 millionth of a second in 100 years. No. That error is huge. If general relativity and special relativity were ignored, then within 2 minutes, the GPS accuracy will fail sufficiently for today's airplanes to land on the airspace. So, bent space-time affects you every day. That's the next basic lesson I want to tell you. Those of students who are interested, you can just Google this fact. by going to Clifford, CLRFFORD, WRILL, and GPS, and you will find the explanation about how these two benefits come about. Okay, so this is the end of the first part. Now I would like to tell you about the second part, which has to do with cosmology. As I said, cosmology began, its birth, modern cosmology began really with the general theory of relativity. Now, as you all know, Newton had this audacity, had this intellectual arrogance, if you like, to think that a laws which govern a falling apple on Earth is also the law, are also the laws which govern the planets moving around the sun. That there is no distinction between the two. Something that we see on Earth is the same as what is happening in the heavens. Remember, you have to go back in those times when most of the people believed that the planets were moving because angels were pushing them. So this is daring, right? And this is the kind of paradigm shift that occurred. Well, Einstein's daring was even bigger. He thought that you could take his field equations and apply them to the universe as a whole. Not the planetary system, but the universe as a whole. Now, imagine, it's only a few years before that people had realized that Milky Way is not the whole universe, that there are also other galaxies. And what Einstein did was, literally took his equations and solved them. He, just as Newton modeled the planets and the sun as point particles, which seems ridiculous the very first thing about it, and they solved the equations, Einstein took the galaxies as dust particles. And the only force between them was gravitational force, a relativistic gravitational force, and used his equations to see what happens. So that was a daring idea, that one can actually take these laws of general relativity and apply them to the universe as a whole. And now what happens is the following. So first let me tell you the story, and then tell you the history. In other words, the final answer is this, and we'll tell you the story about how we arrived at the final answer. Basically, the evolution of geometry is quoted by Einstein's equation, and Einstein's equation tells us that space-time curvature is equal to 8 pi g times the matter stress at 8 times. One uses Einstein's equations, and one uses an observed fact that if you looked at the universe at sufficiently large scales, then there is no preferred direction in the universe, and there is no preferred place in the universe. The universe is isotropic and homogeneous. If you put these two assumptions together, you immediately conclude that geometry must be dynamical and should be related to matter via Einstein's equations, and therefore we got the standard picture that there was a Big Bang and the universe began with a primordial explosion about 14 billion years ago. Now to students and so on, they have learned this, and there's a fact. It's as boring as the fact that the sun rises or something like that. It's just as not true. No, it was not never like that. It was really took a long time to come to these conclusions. Why? Well, a year or 2 years after Einstein discovered general relativity, Einstein and De Sitter solved these equations and tried to construct models of the universe. At that time, Einstein believed that the universe is not time-changing, it's not expanding. So he introduced, to those of you who know, a cosmological constant term, his equations, and then the idea was that here is time and here is space, and the universe is just like that, nothing is changing. And basically, the gravitational attraction in this model is balanced by a repulsive force, effective repulsive force, the cosmological constant, so that the universe doesn't change in time. So there is matter and a cosmological constant. De Sitter found a solution of Einstein's equation, also with cosmological constant, in which there is no matter at all, and therefore the universe sort of comes in like that and goes out like that. So the spatial volumes are decreasing, and then they are increasing up here. But in 1920 to 24, Friedman, a Russian mathematician and astronomer, just took Einstein's equations without a cosmological constant and solved them, and found that there are solutions in which the universe is expanding or contracting. So he looked at the expanding ones, for example. Then the picture doesn't look like this. Picture looks like this. Time is running like that, and this is space. And the space is expanding out here. So if you go back in time, space is contracting. And you go back and back and back, and an instant comes when Einstein's equation tell you that the space-time continuum tears, and if you like, this is the Big Bang, when there is a singularity in which, according to classical general relativity, the physics stops. This is where we get quantum theory of gravity, and this is what my talk in the morning was about. How do you go beyond that in order to do physics, using quantum physics? But this is what was happening with Friedman. it as a mathematical problem, as though he did not really believe physically this happens. He solved Einstein's equation with positive energy density, with negative energy density. He did all those things. Lemaitre, on the other hand, was a Belgian Catholic priest. He was a Jesuit. And he took Einstein's equation, he solved it, and he really took everything very seriously. He did think about the galaxies as just particles. He really thought astrophysically, and he really did think that there is a singularity, and the theory really completely breaks down here. Lemaitre was remarkable, and I think is not enough recognized even now. And he did get lots of honors and so on, but I think he was really seminal in all these discussions. So, but nonetheless, so this happened in the 20s, but still nonetheless, in 1930, there was a meeting of the Royal Astronomical Society in London, at which Eddington, who was the president of the society at the time, sort of raised the question, saying that, well, we only have these two models. We completely ignored this. Only these two models, and then shall we actually put some dynamics into this model? It's static, that's what kind of boring. Or shall we put some matter here and then make a different model? So Eddington's question is typical fashion. He asked the question, shall we put a little motion into Einstein's world of inert matter, or a little matter into the de Sitter premium mobile? Because of premium mobile, because there was no matter, it just came contracted and expanded by itself. Well, it turned out that Lemaitre had already solved the problem. Lemaitre knew Eddington because he had spent a year in Cambridge. And Lemaitre wrote to him, he says, but I've already solved this problem. And I even sent you the paper. And apparently there was one instance in which Eddington was shamefaced, according to Macria, who was a student of Eddington's. And then Eddington quickly recognized that Lemaitre was right. And then a year later, Hubble's discovery came that the universe is actually expanding, and then the statement is that people sort of quickly converted over. Einstein removed his cosmological constant. There's another story about Lemaitre. Namely, Lemaitre went back and told Einstein, don't make it an aesthetic consideration. It's a physical question, if there's a cosmological constant or not. Whereas Einstein always thought it was an ugly thing and had to be removed and so on and so on. And today we know Lemaitre was right. So he corrected Eddington, he corrected Einstein, and he corrected the Pope. So what happened is basically that in 1951, George Gamow, I'll tell you more about Gamow, actually had discovered this thing about nuclear reactions and so on, and come to the conclusion that the universe must have begun with a hot Big Bang. And then he wrote to the Pope Pius. Gamow was a colorful character. Otherwise, I owe a great deal to Gamow because I got interested in physics and cosmology and such things, reading his popular books. So in the high school, I was reading 1, 2, 3, infinity, and such things. He was a very colorful person. So he wrote to Pope. I don't think he was religious at all. He wrote to Pope Pius XII by just saying that, well, look, just like science is also saying that the universe has finite beginnings. Pope Pius XII was excited, thinking that science and religion are coming together, and there was an astronomical meeting, Vatican as an observatory, and therefore there were astronomical meetings there. And that meeting, he sort of, said, well, science and religion are finally coming together, etc. But Eddington Lemaitre had the audacity to go and correct the Pope by telling by the private audience, sort of convinced him that one should keep religion and science separate. And indeed, someone must have convinced him very well. Well, after all, he was a Jesuit, so they know how to convince him. So he, and the Pope then, there was a much bigger meeting, astronomical meeting next year, and the Pope never mentioned this again. So there are interesting episodes that happened. But really, for the longest time, whether to believe in the Big Bang theory or whether not to believe in Big Bang theory was really kind of remained an aesthetic preference, philosophical aesthetic preference. There was a program in Soviet Union led by Lipschitz, Landau Lipschitz, and Kalashnikov and others, to say that, well, this Big Bang was an artifact of high degree of symmetry. If you have a realistic model, solution of Einstein's, which don't have a symmetry, there would be no Big Bang, there would be no singularity. This was shattered by the singularity theorem that was proved by Roger Penrose, and then after that, the whole, this program basically didn't continue. But then something else came, which was the steady state ideas that were put forward by Fred Hoyle, Jay Larniker, Hermann Bondi, Tom Gold, Dennis Sharma. So these people had this idea, these are the leading minds at the time, And they were convinced that, in fact, that the idea of a Big Bang was not something that's very good, and one should really be talking about, one should not be talking about a Big Bang at all. In fact, the name Big Bang was coined by Fred Hoyle to make fun of that idea. Now you start. It was supposed to be a pejorative term, a sarcastic term about this idea. So this is what happened, except that finally there was a transition from mathematics and aesthetics to physics, and this happened because of two things. The first was nucleosynthesis, the second is the cosmic microwave background. So the nucleosynthesis issue is the following. See, we're all made of atoms right here. So where did these atoms come from? Most of them are quite heavy atoms. Where did this heavy atom come from? Well, these are cooked in stars. Stars are ovens which cook these atoms to nuclear reactions. But if you look at more carefully, that's what people did. Hans Bethe, George Gamow, Alford, and so on. They did this very carefully, and they found that if you look at the light elements, particularly helium and hydrogen, lithium, then their abundances that were observed were such that they could not have been cooked in stars. They were cooked earlier on. They were already there before the stars were born. And so the question is really, how did they arise? How did these elements arise? So then the idea came that there must have been some hot early epoch, and then quickly George Gamow realized that this must be the Big Bang model, very, very early universe, where the universe was hot. That is where the light elements were actually cooked. And it fit together very, very well. And it's a very detailed theory. So it fit very, very, very well. So that sort of gave some lot of credence to in the physics community for the Big Bang model. Then there was the issue about cosmic microwave background. So basically, what we see, well, the whole universe is bathed in these electromagnetic waves that are all around us. They are basically like a black body radiation that surrounds us. And if in fact there was an early epoch of a hot Big Bang, then there is a natural way for this cosmic microwave background to have come about. Basically because at the very early time the universe was very hot, atoms couldn't form. As the universe expanded, it cooled down. The first hydrogen atom could be formed, and then so the matter decoupled from the radiation and could flow towards us. And that is the cosmic radiation that we see today. So these two factors changed what brought the Big Bang to the mainstream picture. So here is the cosmic microwave background, and here is the fact basically, this is time, this is space, and the idea is that we are up there, we're looking back, and we find this glow. So if you like, afterglow of a big planet, right, that we see in the hot universe, early hot universe. And so this is really a snapshot of the universe when it was 380,000 years young. So this occurred quite a long time ago. Today it's about 14 billion years. This happened when the universe was only 380,000 years young. And there is a spectacular success for the last 2 decades. People have observed this microwave radiation. This microwave radiation has slight fluctuations. And this say that the density was not completely uniform. It was almost uniform. But there were fluctuations of the order of 1 part in 100,000. And these fluctuations in density grew because you have matter is attracted towards higher density because of gravity and goes away from the places where there is less density. And this leads to basically the large-scale structure. And the cosmic microwave background has been observed very carefully through these 3 generations of satellites. The first one was called Kobe, a cosmic microwave background explorer, launched in 1989. It's followed by the Wilkinson microwave anisotropy probe. It was launched in 2001. Basically, going from here to here, the error bars reduced so much that the parameter space cosmology shrunk by a factor of 30,000. And then there was a similar huge jump in the precision the next time when in fact the Planck satellite was released in 2009. They released their final data a few months ago, and they're still going to release a little more data in the next year or so. So these missions are so incredibly accurate that given us a picture of the universe, very, very early universe, so well that in fact we understand we understand quite well now the origin of this we understand quite well the nature of the cosmic microwave background. So basically, when the universe was 380,000 years ago, the universe was extremely homogeneous as Lemaitre had envisaged, and in today's terms, the temperature is about 2.73 degrees Kelvin. So here is a black body curve, which is you see in textbooks, and these are the observations. You can see that the errors are so small that, in fact, you see this black body curve very, very well. But nonetheless, there are some of these tiny inhomogeneities, which are 1 part in 100,000. And then what happens to the following? That these tiny inhomogeneities seen in the cosmic microwave background, with the universe was about 380,000 years young, grew because of gravitational attraction, obeying the equation of general relativity, and knowing the known physics, the dynamic astrophysics, astrophysics, one can actually show that these fluctuations grow to give us the large-scale structure of the universe we see today, some 14 billion years ago. This is the true triangle, you see. So if you look at 380,000 years, and if you divide by 14 billion years now, that is, in human terms, like the ratio between 1 day and 100 years. So what is the command of physics we have today, astrophysics and fundamental physics we have today, is such beautiful, it's so much is the following. Then in human terms, basically if you were to take a snapshot of a baby, when the baby is 1 year, 1 month, 1 day old, and then I got a theoretical understanding completely, I put it in the computer program, all the laws are known in biochemistry, biology, molecular biology, physiology and so on, as to give me the portrait of the person when the person is 100 years old. Imagine how much you would need to know. We know that for the universe. This baby grew to this height. So it's really very spectacular. I was going to say a few more things about cosmology, but given the time, I will just skip the last part, which is equally exciting, but I'll just skip that and go to the black hole part. So now let me tell you a few things about black holes. So as you know what black holes are, they are regions of space-time from which even light cannot escape. So here is a portrait, cartoon of the small black hole, a few solar masses black hole, and it is gobbling up a star, and as it gobbles up the star, it spews out these huge jets, which are actually seen in the observations. And now therefore black holes, the small black holes, are widely regarded as the engines that will drive most energetic phenomena in astrophysics. Small black holes and a few solar masses black holes. These are widely regarded as. In our own galaxy, in the center, there is a black hole. How do you know it? Well, we look at there is a central region. Of course, we don't see anything there. But we see that the stars are orbiting around it. And as though there was a high mass in the center. And by looking at this orbit, the stars circulate. And they have been looked at for 15 years or so now, carefully monitored. And one concludes that there must be a mass of about 4 million solar masses in the central region, and this is our own black hole, Sagittarius A star. Right? This is the black hole that we have. These are the large black holes, like million solar masses. Now, as early as 230 years ago, as early as 1784, there were ideas about black hole already using Newtonian gravity. And here's a quote from the Philosophical Transactions of the Royal Society by John Mitchell. He calculates Newtonian gravity that you might have a body such that the escape velocity from that body equals the speed of light for that body. And then even light would not escape, therefore they would appear as black. And he concludes that if there should exist in nature any such bodies, we could have no information from sun. Yet, if any luminous body should appear to revolve around them, we might still, perhaps, from the motion of these revolving bodies, infer the existence of the central ones with some degree of probability. Amazingly, that's what we're doing with our Milky Way today. Right? It looks very prescient. And the same thing is true with Marquis de Laplace, wrote his famous Celestial Mechanics volumes, in which he calculated, saying that there may be a luminous body of the same density as Earth, whose diameter is about 250 times larger than that of the Sun, can, by the attractive power, prevent light from reaching us. Consequently, the largest bodies in the universe would remain still invisible to us. So this is what you hear often, particularly students and so on. Therefore, you might think that, well, black holes is nothing new. They existed in Newtonian gravity. This is wrong. This is wrong for the following reason. That in Newtonian gravity, all of Newtonian physics, all speeds are relative, including the speed of light. So the speed of light that is used in this argument is really the speed of light in some rest frame. So one might see is a rest frame of the central object, of the object itself, which is supposed to be emitting light. But if I have an object like that, like the moon for example, sitting out there, and if I shine light on it, as the sun shines on the moon, light is reflected. So as the light falls in fact as it falls in, it should be accelerated, and by the time it hits the surface of the object, it's just by momentum conservation, this light will be able to reflect back. In other words, because the speed c is relative to in the rest frame of this object, really you can just do a two-line calculation to see that by reflection of light, such bodies should be actually observable. Or if you want to give a simple-minded picture, you have got such a body on in atmosphere, there will be atoms moving around, some atoms will be moving this way, emit light, then the speed of this atom is v, plus the speed of light in its rest frame will be c, so the total speed of the light ray will be c plus v, and therefore it will be bigger than the escape velocity, and therefore it will actually escape from it. So in Newtonian gravity, you cannot have black holes. If you are consistent, you cannot have black holes. So what we need for black holes is both an absolute speed of light, which is independent of any observer, and that is what special relativity gives us. And we need gravity, and therefore we need general relativity. So in general relativity, you can have region of space-time. Time is running this way, space is horizontal, and there will be some regions of space-time like that. If there is sufficient matter in these regions of space-time, then you have got these light cones, which are sort of which tell you how light propagates. Light propagates around these cones in space-time picture. So these light cones are far away from the body, would look upright, like in flat space, like if there was no matter at all. But this matter will try to attract, will actually tip this light cones. Light rays will be attracted at here. And a stage comes where all the future directed light rays become attracted to some space-time region. And this occurs irrespective of any observer. There is no relative motion up here. It happens for all observers, and it has nothing to do with and it happens because of strong gravity in this region. So in general relativity, we can have regions in which light is trapped, and in absolute sense, and irrespective of who observes, and curved space-time is really essential for these black holes. Now, I told you about Curie's history in cosmology, that people took a long time to believe that the universe is expanding, and finally, it's really, but the beautiful thing about physics is that you can have philosophical prejudices, and we should have to drive our work. But then finally, observations come and kill an idea or elevate an idea. There, nucleosynthesis and microwave radiation sort of told us that the Big Bang idea was the correct idea. This approximation was the correct idea. So the same thing happened in black hole physics. Namely, there is a curious history. The simplest black hole solution was discovered by Schwarzschild, while he was serving on the German front during the World War I. So very soon after Einstein's paper came in, it was published before the war was finished. And he wrote from the front lines, letter to Einstein showing the solution. Einstein was surprised that the exact solution could be found, but that's what happened. It's an unfortunate thing that Schwarzschild actually died in the First World War because he caught some disease, and he actually died there. But the clear interpretation that this is what represents a black hole, came to await several decades. And I think people in India know very well the Chandrasekhar Eddington episode. Chandrasekhar found that if you have a star which has burnt its nuclear fuel, then it would actually contract. Then it could perhaps reach an equilibrium by balancing gravitation attraction with a Fermi non-degeneracy pressure, because these are fermions, like either electrons or neutrons, and therefore that you cannot put them in the same state. Therefore, there is a certain pressure, quantum mechanical pressure, that comes into the picture. But however, if the star was sufficiently large, its mass is more than 1.4 solar masses, then gravity wins, the Fermi repulsion is not enough, and therefore the star will actually collapse. But Eddington refused to believe it, and Eddington said things such as, various accidents may intervene to save the star, but I want more protection than that. I think there should be a law of nature to prevent a star from behaving in this absurd manner. It's a good lesson for young people, namely, don't take seriously if in fact senior people tell you that your ideas are completely wrong, right? Have persistence, but also be very self-critical, right? Chandra did not just say that I am right and Edict is wrong and go away, but rather he persisted, worked on it for almost 10 years, really developed these ideas in great detail, and then left the subject, right? And of course, as we all know, years later, he won the Nobel Prize for this work. Curiously, Einstein was also opposed to this idea of black holes. So he did a calculation. He took a star or body with perfect fluid, if you like, and he looked at its collapse under gravitational attraction. But he assumed that the star would contract in what is called as adiabatic manner. In other words, very, very slowly, very, very slowly. And then he found that the star would not collapse, that this black hole would not form. But it turns out that this assumption was incorrect, so this calculation was wrong, the assumption was incorrect, because when the star goes, it really goes zoom, right? It's a millisecond that it takes for the neutron star, the solar mass object, to really become a black hole. And therefore this assumption was wrong, and Einstein was also wrong. So Einstein thought that it was impossible to form a black hole through gravitational collapse, but just a few months later, people, Oppenheimer and Volcker, solved this problem and showed that the black holes do form. Curiously, Bergman, as Professor Mukunda mentioned, was an assistant of Einstein, and he wrote this very influential book in 1942 on general relativity, the first serious textbook in English language if you like, on general relativity. And then, the editor had already written, but this is a little bit more modern than any English book. But it makes no mention of black holes. So in the late 70s, there was a widespread belief still that black holes were mathematical solutions with no physical significance. Students of Chandra, my friends, would go to MIT and so on and give talks, and people would listen to them politely, but then the leading physicists would tell them, you don't really believe it, do you? I mean, this is all mathematics, it's not really physics. It's completely changed now, right? Now, black holes are ubiquitous, and they're everywhere. Every galaxy is supposed to have a black hole inside. Now it's a major discovery or a surprise if in fact we find a black hole which doesn't seem to have a black hole inside. So again, things are completely changing. Here is a black hole bubbling up, emitting X-rays as matter falls into it, accelerated charged matter, emits X-rays, these images are seen. Here are two supermassive black holes. These are black holes in the center of the galaxies, and they are on their way to collision with each other. Here is a gamma ray burst. Gamma ray bursts are the most energetic phenomena in the universe. In a few blinding seconds, more energy is emitted than 1,000 suns in their entire lifetime. And these are seen routinely, once a day or once a week or so. So there are many, many of these objects, and the only way to account for their energy is gravitational energy, gravitation. There is not nuclear energy. Any other processes cannot account for this energy. It is conversion. It's the gravitational process which actually caused this. So these are really either collision of neutron stars, which would form such a black hole, or it would be some, it's a formation of black hole of one kind or other that leads to this process. Okay, so then that brings me to the last part of the talk, which is about gravitational waves. And this is particularly exciting right now as we speak. Now what are gravitational waves? Literally, they are just ripples of curvature on space-time. Gravity is encoded in the curvature of space-time, therefore a wave is a ripple of curvature. So this ripple in the geometry of space-time. Now you all know about electromagnetic waves, like this electromagnetic wave which is shining up here. And you can work out how they are emitted, right? So you can have a dipole, and that dipole can oscillate. So I got positive charge and negative charge, and that oscillates, and when it oscillates, you can produce the electromagnetic waves. Well, something similar is true with gravitational waves. Namely, that just as moving electric charges produce gravitational waves, in general relativity, the moving masses produce gravitational waves. So, just as moving charges produce electromagnetic waves, moving masses produce this. Here we did time-changing dipole moments, here you need time-changing mass quadrupole moments. They come in, the gravitational waves come in two polarizations. If you have a bunch of test particles like that, the gravitational wave passes through, then this ring would be deformed in this way for one polarization, and for the other polarization, it would be deformed in this particular way. And Einstein worked this out just 2 years after the publication of his statement. So it was there. But still, for a very long time, this is because of the force. You see, in electromagnetism, you talk about radiation, and that falls like 1 upon R. But what do you mean by 1 upon R itself is determined by geometry. And geometry itself is a dynamical entity in general relativity. So therefore there is a confusion, right? What exactly one means by 1 upon R, and if in fact you are talking gravitational waves in full general relativity. And so there was a great confusion until the 1960s, and whether gravitational waves exist in full nonlinear general relativity, or if they are actually artifacts of weak field approximation that Einstein had made. And surprisingly, Einstein himself contributed to this confusion. In a letter written to Max Planck in 1936, famous one of the founders of quantum mechanics, he wrote, together with a young collaborator, who was Nathan Rosen, I arrived at the interesting result that gravitational waves do not exist, although they had been assumed to be a certainty in the first approximation. This shows that nonlinear gravitational wave field equations tell us more, or rather limit us more, than we had believed before. The weak field approximations, linear gravitational waves, they exist, but in the nonlinear full general relativity, they do not exist. It turns out, it was revealed about 10 or 15 years ago, that the paper actually was sent to physical review, and this was refereed, now we know, by Robertson, of the cosmologist, and Robertson wrote a 10-page review, sent it back, saying the paper is flawed. Einstein was furious, because in German system, like also in France, the members, the fellows of the society, just read their papers, and they just appeared in the proceedings. So the proceedings of the Christian Academy just reproduced Einstein's papers. They were not sent to a referee. He did not know that papers are sent to a referee. And in fact, he wrote an angry letter saying, I sent you this paper to publish it, not to show it to other people without my permission. All this correspondence exists. You can look at it on the web. It's very interesting. And then he withdrew the paper and refused to send any other paper to physical review since then. By the way, in the same year, he published 2 seminal papers in physical review with Nathan Rosen. One is called Einstein-Rosen bridge, and the other one is the EPR paradox. It was the same year that these papers had appeared. And this was the 3rd paper in the series. Well, then he sent it to the proceedings of the Franklin Academy in Philadelphia, which of course immediately accepted it. It was going to be published. They sent back the proofs, and then Einstein realized in the meanwhile that the referee was right. And he changed the article to the proofs, and therefore the proofs, this conclusion doesn't arise. The printed version, the conclusion is not there, but the gravitational waves do not exist. It has disappeared completely in the conclusion. We all know these things because the proofs exist, everything else also exists, and so on. So even Einstein makes mistakes. Make mistakes. So don't be afraid of making mistakes. Of course, not copy Einstein makes silly mistakes, but okay. So then this conclusion was really clear in the 1960s through the work of Hermann Bondi and Ray Sachs. Hermann Bondi had a group in King's College in London, and Roger Penrose, who at that time was also in London. And the reality of gravitational waves in full nonlinear general relativity was firmly established in the 1960s through systematic theoretical analysis by these people. And on the observational side, we know that gravitational wave exists, but only indirectly. Because we got these double star systems, one is a pulsar, the other is an ordinary star, and they are going together, but they are actually emitting gravitational waves because their quadruple is changing. The quadruple moment of the system is changing as they go around, and one can calculate how much quadruple moment should be changing, therefore how much energy should be lost via gravitational waves using Einstein's formula, and then because they lose energy, they fall towards each other slightly. So one can actually see the orbit is shrinking exactly as predicted by general relativity. So we know that, and therefore that's why we know that gravitational waves exist, and that is the only Nobel Prize for general relativity that was given so far. So we know that they exist. But now the ambition is much more. Namely, the idea now is to detect gravitational waves directly on Earth and create brand new type of observatories which didn't exist before. All the observatories we have so far, all the knowledge about the universe we get is through electromagnetic waves. It could be visible light, it could be infrared, it could be X-rays, it could be gamma rays, it's just electromagnetic light. Now, with the gravitational wave observatories, they will bring a signal in the form of gravitational waves. So a brand new window in the universe is now available. It's a tool to probe the most buoyant or energetic events in the universe, such as black hole collisions, supernovae explosions, gamma ray bursts, and so on. Gravitational waves will provide detailed images that we cannot be obtained from conventional astronomy. The photons emitted from there scatter a lot and lose their memory. Gravitational waves interact very weakly, and they bring us a faithful picture of the spectacular events that are taking place in the universe. Now, so far, we have got these observatories, as I will see in a second, but so far they are not detected in the gravitational waves. But the observatories are sufficiently sensitive now. Now we do know that there are very, very dense objects nearby in our galaxy. The Crab pulsar. This is the explosion that the Chinese astronomers have noted, occurred in 980, I think, AD. And that is the pulsar. It's a neutron star. It's an object like that. And supposing there was a mountain in the pulsar, which is just a meter high. If there is a mountain which is a meter high, then as the pulsar is rotating, the quadrupole moment of that object is changing. Therefore, it should be emitting gravitational waves. The sensitivity of the detectors until last year was already high enough that they should have seen these waves. They don't see these waves, which tells us that there are no mountains or crab which are higher than a meter. I mean, it's amazing, right? That we can put this science together to say what is happening out there in the universe. And that, by the way, tells us something about the equation of state of nuclear matter in the neutron stars. It's fantastic the way that this science are fused together. Today now, there are brand new types of observatories. In the US, the National Science Foundation has built two that are called LIGO, Laser Interferometric Gravitational Observatories. And Europe has built one, which is Virgo. And laser beams, what they have is laser beams, which go around 4 kilometers, reflected back, go around 4 kilometers, reflected back. If a gravitational wave comes by, it will shake the mirror at the end of this cavity up here, and that shaking of the mirror will destroy the interference here. Therefore, there will be fringe shift, and we can measure how much fringe shift there is. This is really state-of-the-art technology. One is talking about measuring displacements of the mirror of 10 to the minus 13 centimeters, nuclear radius, right? Radius of proton. No one can actually do that. The sensitivity now is really the required sensitivity has been reached now. There is a synergistic interplay between fundamental science and the state-of-the-art technology involving general relativity, astrophysics, statistics, cyber science, high vacuum physics, suspension systems, lasers, and optics. You have got laser beams going 4 kilometers coming back. We have got high vacuum, highest vacuum that we have on Earth. And now it has reached the desired sensitivity. The engineering runs were finished. The science runs had just begun. And amazingly, you might have seen this last week, there was an article in Nature, almost 2 pages long, which was based on a rumor. At least I have never seen an article reporting a rumor. And the rumor was supposed to be that they might have seen the first gravitational waves. That's why it's so exciting that they might have seen this. And therefore, this is so exciting because it is opening a new window of the whole universe. It might change our view of the universe in a dramatic fashion. And fortunately for us, in fact, there is a golden opportunity for India. India has been invited to join the global network of the gravitational wave observatories. NSF of the United States is agreed to provide an advanced detector of about $80 million. And DAE and DST are supposed to build a LIGO India observatory, which will cost about $200 million. The DAE request is pending at the cabinet level. And this high-profile international collaboration featuring a consortium of national labs and institutions has been formed. It is led by Indigo, which is right here in this institute, Bala Iyer. And Ayuga is leading the data analysis for exact science. The IPR at Ahmedabad is leading the work on vacuum systems, and RRCAT in Indore is leading the work on lasers. So this is going to be developing and deploying the highest caliber state-of-the-art technology on the Indian soil to unravel the deepest mysteries all the way from the far edges of the universe. I think this is really an extraordinary opportunity to develop human resources in a variety of cutting-edge fields in pure science as well as technology, and a chance to participate in the front ranks of the greatest revolution that was unleashed by Einstein's ideas. So I really hope that this request is granted soon, so that actual work will begin and India will be able to participate in this key moment when the new windows of the universe are getting open. If India is one of the active participants, that would really be fantastic. Okay. Einstein 100 years ago was quickly recognized as a supreme triumph of human intellect. Paul Dirac, one of the founders of quantum mechanics, called it probably the greatest scientific discovery ever made. For 8 years, 1907 to 1915, Einstein had been consumed by the tension at the foundations of physics. And by not letting go and working persistently, he had learned new mathematics, developed new concepts, do hard calculations, he discovered a theory that represents an unprecedented combination of mathematical elegance, conceptual depth, and observational success. The process carries many lessons for younger researchers up here. Don't give up. Max Planck comes and tells you are wasting your time, you don't believe it. Right? If you believe in your idea, then push it. But be your own critic, right? Your worst critic. Try to punch holes as much as possible, not just be blindly follow the idea. And if you don't see anything wrong with it, just pursue, and you might find something fantastic. The decades have passed, and new aspects of revolutionary paradigms continue to emerge. We've seen the Big Bang, the black holes, the gravitational waves. And now a century has passed since Einstein's discovery, and yet every researcher who studies general relativity in a serious manner continues to be enchanted by its magic. I had an occasion to give you a glimpse of bird's eye view of few of the samples up here. There are many, many things that are happening that are illustrated by pictures up here. In particular, there are developments in mathematics I did not go into at all because they are somewhat technical. But general relativity has provided impetus in so-called geometric analysis by providing new topological, new invariants on metric manifolds. And this has become a real standard tool in geometric analysis now. Similarly, in computational physics, general relativity, this gravitational wave physics, has pushed the frontiers, really, of computational physics itself, both in numerical simulations and data analysis, and in quantum physics, we're bringing together general relativity and quantum gravity, and cosmology and astrophysics. So there are many, many things that are left out here. If you want to read more about it, there's a volume which was published just a few months ago to celebrate 100 years of general relativity and gravitation, a centennial perspective. It was commissioned by the International Society, and it was released in 2015. And it has 4 parts, and these 4 parts are Einstein's triumph, cosmology, astrophysics, and other applications, gravitational waves, a new window on the universe, mathematical applications, gravity, geometry of throw, and beyond Einstein, the quantum physics. Each of these parts has an introduction written by the editors. In about 10 pages, it summarizes what has happened. And so this is really a very useful